Have you ever just looked at a giant ship out on the ocean and thought, how is that even possible? It feels like it breaks the laws of physics. Well, today, we're going to dig in and unravel the simple but super powerful secret behind why some things float and other things sink. I mean, seriously, just think about that for a second. We're talking about a floating city made of steel. It's this massive, colossal hunk of metal. And yet, there it is, just bobbing along on the water like it's no big deal. It just doesn't seem to make any sense. And then, on the flip side, you can take this teeny tiny little pebble, toss it in a lake, and float straight to the bottom, no hesitation. So what on earth is going on here? How can something so huge float when something so small sinks? Well, the answer to this whole puzzle, the secret that unlocks this entire mystery, really just comes down to one single elegant concept. And that word is density. All it is, really, is a measure of how much mass, stuff, is crammed into a certain amount of space, or volume. And this right here, this is the key that's going to unlock everything for us. The easiest way to think about it is like packing a suitcase. You could fill that suitcase with fluffy pillows, right? Or you could take that exact same suitcase and pack it with heavy books. The suitcase full of books has way more stuff packed into the same space, so we say it's more dense. And of course, science has a neat little formula for it. Rho equals m over v. Now that weird-looking p is actually a Greek letter, rho, and it just stands for density. M is for mass, and v is for volume. It's a really simple idea, but understanding it is the key to this whole thing. So if we're going to solve the mystery of the floating cruise ship, we need to know how to actually find the density of things. Let's get our detective's toolkit together and figure out how to measure it. Okay, for a simple shape like a wooden block or a cube, this is a piece of cake. You just weigh it to get the mass. Then you measure its sides, length times width times height to get the volume. Plug those two numbers into our formula, and bam, you've got the density. But what about things that aren't perfect little cubes? I mean, you can't exactly take a ruler to your house keys or some weirdly shaped rock you found, right? So, how do we figure that out? The solution is just brilliant. It's called water displacement. You find the object's mass like normal, but to get the volume, you just sink it in a known amount of water. The amount that the water level rises, that's the object's volume. It's such an awesome trick that lets us find the volume of literally anything that sinks. And hey, we can do this for liquids too. You just have to weigh a specific volume of it. The principle is always the same. Find the mass, find the volume, and you've got your density. Okay, our toolkit is ready to go. We know what density is, and we know how to measure it. We've got all the clues we need to finally crack the case of the floating ship and the sinking pebble. And here it is. This is the golden rule, the whole secret right here. An object will float if its density is less than the density of the fluid it's in. If it's more dense, it sinks. That's it. That's the whole game. So let's look at the evidence. We use water as our baseline, our standard. Its density is exactly 1.0 gram per cubic centimeter. Now look at the others. Oak wood is 0.75, ice is 0.92, both less than 1. But aluminum, it's 2.7, way higher. Okay, so let's test our rule. We've got a piece of oak wood, density 0.75. We put it in water, density 1.0. Based on the rule, what do you think is going to happen? You got it. Since 0.75 is less than 1.0, the wood is less dense than the water, so it floats. The rule holds up. Perfect. All right, round 2. A chunk of aluminum. Its density is 2.7. That's way higher than water's 1.0. So, what's the verdict on this one? Of course, it sinks like, well, a chunk of aluminum. It's much denser than the water, so down it goes. The rule works perfectly. So now we can finally solve our cruise ship paradox. And here's the big reveal. That giant steel ship floats because it's not a solid block of steel. Think about it. The hull is shaped to hold a massive, enormous amount of air. So when you take the average, the mass of the steel plus all that air, spread out over the ship's gigantic volume, its overall density is actually less than water. It's basically a giant, cleverly shaped steel bubble. So now that we've totally cracked that case, let's take this idea to the next level. Because density also explains why some liquids, if you try to mix them, just won't. They stack up instead. Check this out. We've got three liquids you probably have at home. Honey is the densest at 1.42. Water, our baseline, is 1.0, and vegetable oil is actually the least dense at 0.92. So, what do you think happens when we pour them all together? If you carefully pour them into a jar, they will not mix. They'll settle into these perfect layers based on their density. The honey, being the most dense, sinks right to the bottom. The water floats on top of the honey, and the vegetable oil, the least dense of all, floats right on top of the water. It's so cool. So there you have it. From giant cruise ships to the dressing on your salad, density is the secret code of the universe that decides what sinks and what floats. It's never just about weight. It's about how much that weight is packed into a certain space. We've seen how this all works in water, right? But the same exact rule applies to any fluid, and that includes the air all around us. Which brings me to one last question for you. A hot air balloon is huge, and it floats. So, according to our rule, it has to be less dense than the air around it. The real question is, how do they make the air inside the balloon less dense than the air outside? Something to think about. Thanks for joining me on this one.